Hey there, ladies and gentlemen, boys and girls. Today, we are going to talk about another method of how materials can pass across that phospholipid bilayer, that cell membrane. Today, we are going to talk about the infamous osmosis. All right. So we're going to talk a little bit about what is osmosis. We're going to identify what it is. We're going to talk a little bit about how it works, some of the similarities to some of the other things that we've talked about. And then talk about how it's a little bit different. All right, there's a lot of similarities, and it's those differences though that make the difference. Sorry. So let's recap a little bit what we have here when we talk about cell membrane. I have a little small section of my cell membrane, that phospholipid bilayer, that 2 layers of phospholipids. Remember that those lipid tails are hydrophobic, and the phosphate heads are hydrophilic. So we have water on the outside, inside of the cell, and no water on the inside because those tails do not like water. All right, and embedded in that phospholipid bilayer are proteins, what we call transport proteins, proteins that allow things to go in and out of the cell. All right, certain materials to go in and out of the cell. All right, so today what we're going to talk about before we get into osmosis, let's kind of recap what we've talked about. Let's use this example of I just ate breakfast. All right, I just had breakfast, and one of the things I had for breakfast was orange juice, delicious orange juice. All right, and the sugar that's in orange juice is fructose, which is a couple glucose atoms bonded, or glucose molecules bonded together. It's a type of sugar. It's a very large sugar. All right, and so I just drank. Let's say this is the outside of my cell, and here's inside my cells, my intestinal cells. As I just drank that fructose. So I'm going to use fructose. I'm going to, I'll draw them like this, all right, because they're big, large molecules. All right, so I just drank a bunch of fructose. So it means on the outside of my cells, I have a very large concentration of fructose going on. All right, so I got a lot of fructose, and let's say that's a lot of fructose in comparison to what's inside my cells. All right, let's say inside my cells, I have a smaller concentration. All right, so what we're talking about right now is we have things inside the cell and outside the cell. Let's say I have I definitely have let's say outside the cell is now a solution that is 30% fructose. And inside the cell, I have a solution that is 10% fructose. Okay, so now I say a solution of. Remember, going back to what a solution is, it is made up of 2 parts, the solute and the solvent. Everything we've been talking about so far up to this point, this very moment, has been about the solute, oxygen molecules, carbon dioxide, ions, in this case, fructose. All right, we've been talking about the solute. All right, and if we've been talking about diffusion, this idea of diffusion is when cells go across the membrane from a high concentration to low concentration, and it doesn't require any excess energy to do that, right? Rolling the ball down the hill, all right? So right now, this is a large molecule. Because it's a large molecule, diffusion says this would be facilitated diffusion because it's going to need a transport protein. That fructose is going to go from high concentration to low concentration. All right, so it go through there to try and get that balance. All right, what it's trying to do is trying to find that balance between 30% and 10%. Right? If it gets to like that 20%, it's never going to be quite perfect. It will get down to 21, 19, and then maybe back the other way, and it kind of goes back and forth. It's what we'll call equilibrium, dynamic equilibrium. We're balancing it. All right, but we go from high concentration to low concentration. That's what we've done so far. Today we're doing the other half of the story because this is just about solutes. All right. That's only 30% fructose and 10% fructose. Now I got to think about the other part of the solution, solvent. I talked about the universal solvent, and so 99% of the time we're talking about water. All right, talking about water. All right, so in this solution here, all right, I have 30% fructose. That's my solute, which means the rest of it is going to be my solvent. All right, so I have in here water molecules all spread out. H2Os. All right, if this is 10% or 30% fructose, that means it must be 70% water. All right, so I'm doing the other half of the solution now. That's what we're talking about here. All right, and if I have down here, because this is 10% fructose, there's not that much solute. There's not that much solute, but there is going to be a lot more solvent. All right, there's a lot more solvent. Bring it a little bit closer here. All right, so I have a lot more solvent. So this is going to be 90% water. Osmosis is the diffusion of water. All right, so let's think about what that means. Let's think about what we know about diffusion. And all right, osmosis is simply the diffusion of water. All right, so it's kind of doing everything we've done so far about diffusion, simple and facilitated, but this time we're talking about the water. All right, so diffusion we know means we go from high to low concentration. High to low concentration, all right? And we know that it goes from high to low concentration and no outside energy needed. All right, to do that. All right, we're rolling the ball down the hill. All right, so it means we're still going high to low. So osmosis, although the fructose through facilitated diffusion, the transport protein, is going from high to low concentration this way, the water is going to go from high to low concentration. All right, so it's going to go from 90% water to 70% water. That water is going to go from this side of the cell to the other side. But there's a problem, right? That water, it can't go through it's a small molecule, but it can't go through the membrane. Take a second. Think about why can't it go through the membrane? It's a small molecule, just like it's only 2 hydrogens and oxygen. Take a second, think about it. Why can't it go through the phospholipids? Why can't it go through the phospholipids? It's because those lipid tails are hydrophobic. Those lipid tails are hydrophobic, which means they do not want to be by water. And so those water molecules cannot go through the phospholipid bilayer. They need a transport protein as well. And there's a very specific one that does that. That water is going to go from high concentration to low concentration. That protein that allows that to happen, that are embedded through that phospholipid bilayer, is called aquaporin. Porin meaning hole, aqua meaning water. It's a water hole. All right, it's a hole for water to go through. All right, again, another opportunity to just break down the word. All right, so now we have this what we call dynamic equilibrium. All the solutes are going this way, all the solvents are going this way, and eventually this picture is going to be upside down. If all the water rushes out here, and all the solute rushes in here, all of a sudden, this picture is completely upside down. And then it's going to go back the other way. All right, this idea that things are always going to be kind of being back and forth. It's going to go that way, this way, and then back the other. It's going to go back that way, and come back this way. We're trying to find that balance. All right, that 50-50, but we're never quite getting there. Every time we go down one, the other one goes up, and then we kind of trying to find that balance. And every time I take an extra drink of orange juice, I'm putting more fructose in there. And so all of a sudden I'm changing the levels back up again. We're trying to find that balance, or what we call dynamic equilibrium. This is what we're called dynamic equilibrium. Dynamic meaning moving, equilibrium meaning balance. All right, it's trying to find that balance, that 50-50, but it can't ever quite get there because we're always changing new things. If the cell next to this one breaks apart, all right, it's there's a lot of processes that can do that. The cell dies and it falls apart and it releases all its contents. All of a sudden, the cell next to him has a bunch of contents right next to a high level of solutes and solvent. All right, there's a lot of things that are happening. It's never quite getting there, but it's trying to find this balance. So now we have diffusion of solutes through simple and facilitated diffusion, and now we have diffusion of water or the solvent. Both of them are diffusion, which means high to low concentration and no outside energy. That's what they have in common, right? Because they are both diffusion, but it's a difference between being the solutes versus, the solvent. So osmosis is the diffusion of water. All right. In my next video, I'm going to talk a little bit about how this impacts the size of the cell, but that's going to stop us right now about the mechanics of how diffusion works. All right, take a moment to look at that. How diffusion works, about how we go from the solutes will always go from high to low concentration diffusion, but osmosis is that diffusion of water. So we're going to look at the other half of the solution. All right, we go from high to low concentration through a protein called aquaporin. All right, that's going to be it for right now. Thanks for watching, and good luck, and may the science be with you.